So I was talking about reversible computation, and mathematics of this can be completely formulated in terms of permutations. Because reversible means nothing is created, nothing is lost, all you are doing is rearrangement. And the permutation group is a powerful construction which has many consequences, and I will point out just some of the features. That it is a group, that means the inverse already exists, but much more than that, every group can be described in terms of what are called generators. The simplest transformation, then you put them together to build arbitrary complicated operations, and in case of permutations group, the generators can be chosen very simply as exchanges of two objects. Okay, and any arbitrary permutation can always be broken down into a sequence of two state exchanges. It's quite obvious, but if you are trying to write down complicated transformation, sometimes it is useful. So I will just give an example that suppose I start with the configuration 1, 2, 3, and I want to go to some other stuff which looks different, say 2, 3, 1, whatever it is, simple enough. So how do I do that? Well, I can first exchange this of first two. So I will write that as a permutation of the first two objects, which will give 2, 1, 3, and then I exchange the second and the third object to get over there. So in general, any arbitrary thing can be constructed, and many of the so-called elementary gates are these generators in certain sense. So you can put a sequence of them together to construct arbitrary operations. So that is one feature. The other feature is how many of these operations are there. They can also be explicitly listed. So suppose I have n bits, which means that there are two to the power n states, which can be described with that. And then these states, how many ways I can write it? It is the factorial of the number. Okay, so the operations which can perform actually go very rapidly, but you have this simplicity that everything can be broken down into two state exchanges, no matter what number appears over here. And what I described last time was the simplest case of 1 and 2. So n equal to 1, well, 2 factorial is equal to 2, and there are only two operations which we can easily write down what they are, identity and not. But just the next step, n equal to 2, is 4 factorial. There are 24 possibilities. and one can write them down by brute force. Okay. It turns out that they can be expressed as a linear operation x so here these are 4 states. These are 4 constants and these are 6 metric. How many different ways I can arrange these many states? Huh?
If you're working with bits, we have only 0 segments, right?
Yeah.
Most of them will be.
It will be a list like this, permutation of so many objects in the list. Zeros and one, you are writing it as a particular representation of the permutation operation. But the operation acts on a list. So 2 raised to n are the possibilities of the objects in the list. And then there are so many matrices which will shuffle them around. Okay, so for 2 bits, it turns out that they all can be written in this rather restricted form. And it's quite obvious from that it cannot generate any operations like NOT and OR because they are nonlinear, essentially. This all stuff is linear. So, necessary to go beyond just looking at 2 bits to be able to cover the Boolean logic operations, and I gave some convenient choices in the last lecture, like this Toffoli gate and Friedkin gate and switch gate and things like that. There are some sort of generators out of this particular list. Yeah. NOT is also a linear operator on terms of operating on the states. It flips just a permutation of 2 objects, that's all.
You said since this is a 4 constants, right? Can we switch it 4 matrices and 6 constants? Is that possible?
No, you can always write any 2-bit permutation in this form. Constant just simply just amounts to translation, but it's a 4-bit object, so it is.
The question is, so 6 into 4 gives 24. 6 into 4 will give us 24. This is why there are 6 and 4.
Yeah.
Can we write it as 4 matrices and 6 constants?
Not possible.
It has to be this way.
This is you can do a brute force construction and you will find this.
This is only.
Okay.
Here, number of generators. How many number of generators in this case? Because we have 24 permutations.
Generators are 2-state exchanges, and they have to cover the list from one end to another. So at the most, they are n-1. Exchange first and second, second and third, third and fourth, etc. You can have all combinations, and that is enough.
And in this, in the case n equal to 2, you told that R and gate R is covered. R and not, how many gates can be covered? And R not, are these covered?
Everything is covered with two-state exchanges. That is the meaning of generator. Even though the states may be too many, suppose there are here there are say 2 raised to n states. I want to cover it just a binary exchanges and 2 raised to n minus 1, which go all the way from one end to the another, and that is enough.
Means each gate corresponds to each permutation.
Exchanges, binary exchanges are permutations, but they are very simple permutations. Okay, so, well, so in some sense, when you go beyond it, you have to add extra space. Because this was 2-bit operations in the Boolean logic, you are adding some extra space to make this complete, and so you are paying a price. It's not coming for free. And then there are questions about how much is the extra price, and that varies. I will give a couple of examples. One of them I already gave, so extra. So the example which I gave in the last lecture, that the simple operation of swap, I wrote down 2 codes, the one which required an extra space, one which did not require an extra space. I wrote it for any general arithmetic, but it's true in the Boolean logical. Another example which I would like to illustrate is a continuation of these control operations which I defined last time. So, yeah, let me consider this operation which is still higher up in the list than whatever I load down here, and it will give a breakup. There are 3 controls and a knot. So the job is to take this that last bit will flip provided all these three are equal to 1. Okay. The control knot had just one control, control square knot had two controls, and this is the next one is the hierarchy. But this you can break up in terms of simpler operations. The other ones are certain ones I cannot, because C square knot is actually equivalent to constructing AND operations, and it was not possible to simplify, but this one can be, and we can easily see that. I will write it down in terms of there's a C square knot operation and some dummy variables. So this is x, y. I have to give some label to this. Let me call it w. Then there is a z, and then there is a t. So okay. I will put a specific value that the initial register for this extra bit is equal to 0. So what will happen? So this will give x, y, they are all controls, but this is the C square knot. So here I will get 0 plus xy, which is equal to xy. Now I will use another control square knot on these three bits. So it will give now t plus product of the two controls, which is x, y, z. Okay. So this higher order control knot can be broken up by using some extra space into smaller operations. And this is true for any higher order operations beyond 3. 3 is sufficient to generate the full Boolean algebra, and you can do this. But now I can ask, can I do something more? Okay. In the sense that I'm using this extra space. What if this thing is not initialized to 0? Is it available? Because that is again a condition that I'm using some extra space, but assuming that it is blank. Maybe it had some arbitrary value sitting inside it. Can I bypass that also? And it is true that even that can be bypassed. And that again I will give a little circuit. Some extra work is needed. So this is x, y, now this was w, this is z, and that is t, and now I do this, but I don't know what was sitting inside w, so it will be w plus xy. And now I do the same thing, which is over here. So it will give me t plus this xyz is something which I wanted, but there is some extra stuff which came in, which is w times z. And I can then figure out how to cancel this extra stuff. Okay, so that is something which can be achieved. There is no unique solution. You can cook up your own solution. I want to get, instead of w plus xy here, just w. If I do that, then I can add this wz and cancel this extra stuff. But to get this w back again, I need to repeat this initial stuff. So then this is back where it was, and now I can put another c square naught and get rid of this term. Okay, so in this particular case, I had no idea what w was, but still I got my result. The penalty is that you have to put in some extra operations. But given that freedom, you don't have to worry about what is in the extra space. It can be something unknown and you can still work.
Okay. Swap can be performed without extra space, and how come it's an extra cost?
This location of w is extra cost, no? It was,
Swap can be performed without extra space.
yeah. This is not swap. This is a different operation. Swap I wrote down in the last lecture. The three exchanges which did the job.
With 3 bits, we don't need the extra space, right?
Swap is a 2-bit operation only, and it can be done without extra space. It's the non-linear ones. These are ones which require extra space. Swap is not in that category. That's all. So there are lots of tricks one can play with to give some limits about, yes, extra space is needed, but what are the properties of the extra space, how much you require in what particular operation, whether it has to be initialized, not initialized, all possibilities can be tackled. Okay. So now comes a general question that I want to consider a very generic algorithm which can be broken down in many different ways with some elementary gates and some scratch space, etc. What is the extra cost that I need to pay? And there is a simple answer which is important from the point of view of connecting this strategy to thermodynamics. The reason being that we are manipulating certain information. Permutation actually doesn't destroy anything, and so the change in entropy is 0. Now if I want to ask that I really want to run a computer, where is the price that I actually pay going in? And there is a lower bound. So there is a minimum cost that you need to pay, and that is intimately tied to the principle of thermodynamics. How much is the entropy going to increase? And rather, much more specific than which is the particular step that increases entropy. So I can now rephrase everything in that particular setting, and it's rather simple structure that I can write down. It's a block diagram, rather schematic, but there is a input. Then there is a work area, and I need a result to be written somewhere, so I will just take a blank space, and this stuff goes into some machine. So I'm calling it M. What does this machine produce? Well, we want it to have some output, which is the result of the computation, and there will be lot of this scratch space which will cover everything that is not observed. Okay, it's transformation of this work area into some other stuff. And what I want is to demonstrate complete reversibility. So I want to get back where I started. And that can be easily done by saying that I will apply the inverse transformation. And then what will I have? I will basically get back the input and work area, but then I have lost this output which had to be extracted at some stage or other, and that is where I use this blank space with a control not operation. Remember, control not operation acting on value which is 0, that copies it. And so what I have, whatever initial stuff was there, everything came back. But I also have the output, which was the purpose of running this whole algorithm. And the whole stuff is reversible. So where does the cost go in? And the cost now can be looked upon that yes, I run this machine, that is fine. But now I want to run another program on this machine. What will I require? That I will have to erase this output to the blank space and run the algorithm. And that step of erasing the output is the minimum cost which has to be paid. And the cost is labeled as free energy in terms of computation.
One question, can we consider work area as some kind of input?
Yeah, it is some input, as I gave an example, some extra space.
So actually, technically, no difference between input and work area.
Input is the data you are putting in, work area is just some extra space. It may be initialized to 0, it may be just something arbitrary, you have no idea what it is. The point is that whatever it is, it's completely recovered. And that is why you are not paying any cost for it.
that means theoretically speaking, whatever energy the machine consumes for the output, the input to output, in the reversible process, the energy is going back to us from output to input.
Yeah. To run this, there is no lower bound. Of course, whether you can reach it in practice or not, that's a different story, but it's a lower bound.
We explain once again how is the ratio of output.
This is the control not operation, which will copy whatever is here onto the extra space, provided the initial value is 0. At the end, I have recovered everything except that the 0 got replaced by the result. That is completely legitimate. The only thing is I want to not just run one program, but run other programs also, and every time I do such a thing, I will have to erase the output, put it as a blank space, and that eraser is the irreversible operation. That is where the cost is going. So and if you have studied some thermodynamics, well, part of the physics, there are many paradoxes listed in the connection with entropy. One of them is known as Maxwell's demon. Maxwell's demon. And this is exactly analogous to that. In thermodynamics, this paradox appears that if you have a Maxwell demon, you can run processes without any change in entropy. But then the question comes that, yeah, the Maxwell demon cannot keep on storing all kind of knowledge in its memory. You have to wipe out the memory once in a while, and that is where the cost of the entropy is buried. Yeah, if I put everything together, it's reversible, but I have to keep on doing something to continue working further and further. And Maxwell demon does the same thing. It looks at various configuration and then decides what to do. That is fine. But then you have to look at the configuration again. And for that, you have to erase the previous memory, put in the new one, and decide again based on that. So this is the fundamental understanding of what really happens in irreversible processes and where is the ultimate cost going in. There are various labels for it, and sometimes in the context of computation, this thing is also referred to as Landauer's principle. Of information processing cost. Where is the cost? The cost is in the erasure, not in anywhere else. Yeah.
Doesn't copy will consume any energy or cost?
Yeah, copying is a control not operation, it's reversible. Of course, in practice, some of this stuff is not really implementable. So what is done, or what people are trying very hard to do, is recycling. You may not save everything, but save as much as you can. Okay. It can't take you all the way to here. And for example, in electrical circuits, there is a capacitive part which is used for charging and discharging, and that you can recover by connecting to some reservoir which will store the extra charge and then bring it back when necessary. But then there will be resistive stuff that is lost. So people are actually designing lots of semiconductor devices where you try to save the energy. The reason being that resistive part produces heat, and that is a major disadvantage in the miniaturization program. How do you take out heat? And these are techniques of this recycling, try to control it in some manner or the other.
Choice of machine and processing quality improved by KI blank space. So there's some cost in terms of energy and some cost in terms of number of operations.
Yeah.
So when we say no other free energy cost, by using the reversible processes that requires no other free energy other than my removal of the output.
Yeah, so for this structure, I can write down what the cost is. So let's irreversible algorithm of some number of steps. Let me call it T. Each gate is going to replace by one of those analogs with little bit of extra space. So what will become of these things in this particular scenario is that you have a reversible algorithm with number of steps doubled because I am using M and M inverse. And what you call order tree extra space. Each gate will be replaced, some of the 2-bit stuff will be replaced by 3 bits. And that is the maximum that can happen, and I can just count every gate, whatever it is. I will, instead of using them as 2-bit gates, I will put at 3-bit gates, and there is an overestimate, but that is the maximum extra space I need. And that explicitly quantifies the cost. Now one can ask, can I make it a little better in various ways? And things like this, tricks will tell you that I can try to reduce the space, but if I do that, then I will have to pay some penalty in some way or the other. And one of the possible example is to compare it with what is done in a scenario of parallel computation, that I can always reduce the space by converting the parallel computation to a sequential computer. That is always possible. The other way around may not be possible, it depends on the algorithm, but any parallel computation can be converted into sequential computation, and that allows you to reduce the space. Time goes up. So there are trade-offs of that type, and well, one can play with that to certain extent. So and it's better to give one example, well, in a quick summary. Yeah.
Erasure in the eyes of C0 gate is the second part, that is the reversible. Then how can we consider it as a free cost? Like in the entire machine,
Yeah.
we are going from line space to output, which is
Yeah.
the forward. The erasure in the eyes of C0 gate is output to line space. So it's the second part of the total process, reversible. Then how can we consider it as a free cost consumed?
Nothing is consumed at this stage. The point is that to solve another problem, I will have to erase this output and convert it to a blank space in the next run of the computer, not in this particular run of the computer. That is where the cost is. It's postponed, but that is because you want to use it repeatedly. Yeah. So the example is basically tells you what is important in the reversible computation. That suppose I want to go from step 1 to 2 to 3 or whatever it is. The idea is to reduce the scratch space, which means I don't want to wait till all the T steps are executed to erase the space. I can do this inverse operation somewhere in between and get rid of the extra space. The point is that if I do that, I don't want to lose the part which is required for computation. But if something is erasable, I will do it immediately and it will make some work area free which can be reused. Okay. So what does reversibility require? That if I am going from 1 to 2, I should be able to go back from 2 to 1. And so whatever work area is required here, I cannot get rid of it. But now look at the next step, that I want to go from 2 to 3. And reversibility require that I should be able to go from 3 to 2. But at that time, the work area which is required between 1 and 2 can be released, because its job is over as long as I have a full information about what is there in 2. Okay. So if I write some transformation, and it can be done like that, that I need at least the previous result completely, because without that the reversibility will not be there. But what is long back in the past, that I can keep on freeing up by the operations. I can write this as the machine going from 1 to 3 is equal to machine going from 1 to 2, machine going from 2 to 3, and then I can apply the inverse operation of whatever done was over here, because all the information of 2 and 3 is available. I can drive back from here and that will free up all the areas. So this is schematic, but it allows you to understand what is important, and then I can iterate this procedure. Actually, iteration is not the best way of doing it, but a recursive manner actually is much better. And that requires some amount of algebraic work. You can actually find the full description in John Preskill's lecture notes. I will give you the answers, but because that is what is important. This that it will give you an exponential advantage as far as the amount of space is concerned. From being of the size t, you can make it log t, but time goes up because what I am doing is spending extra time for every operation. This was originally 2 steps, but now it is 3. Okay. So time goes up by well, every factor of 2 gets replaced by a factor of 3, and you can write it as an exponential scaling of time to the power, which is log 3 by log 2. You can actually do better and bring it back much closer to t raised to just 1 without using the log. So there are various kind of rearrangements you can do. Here I just choose 2 steps forward and 1 step back. There are other rearrangements where there will be L steps forward and L minus 1 steps back. If you play around with this thing, the extra power of t actually be brought down very close to 1. So there is a penalty, but there is also a saving, and it just says that space can be reduced exponentially and the time goes up by a little more in the power of whatever it is. This is a trade-off, but it is something which emphasizes what is important in reversibility. Yeah. Yeah. Yeah.
We are freeing up the work area for real. That means the term at universe 1, 2 represents the freeing of work area.
Yeah.
But then the information of 2 is lost after reversing. How can we say keeping all the information?
No. 2 is whatever the data is there in 2 is still present. I am
That is converted to 3. That's when
because both 2 and 3 are present, and that is why it remains reversible. Because I need both the steps. The final step is now 3. From 3, I should be able to go back, and that requires that the data for the 2 is still present. If it is present, I can go back. But there is no need for this work area, which was required in 1 and 2, and that can be erased and you can use it to something extra. So it's a recycling in some particular sense. And now I can just write down what is going to happen in the quantum case. We'll come back in more detail a little bit later, but all the ingredients are already present, that if I can do reversible computation with a set of binary variables, I can identify those binary variables with the basis of the quantum states. What is extra in the quantum state? That I can perform superposition. Basis states are already there, completely described. So and what does superposition require? That the transformation should be linear. If I have a linear transformation, 1 plus 2, if I transform it, there will be just one transform, second transform, just addition of the two. So this whole circuit and the operation will go through provided the transformation is linear. The superposition will just be completely carried over. And it is linear. The way all this permutation structure is concerned, the transformation is linear, and so the same circuit implements quantum logic. Nothing more than that. Just label these Boolean states as the basis vectors. The transformation is linear. You don't need anything more. Yeah. The algorithm will exactly be the same thing in whatever is done in the reversible logic. It will solve the problem. All I have to ensure is the states which are available in the physical space allow superposition. And well, then why are you worrying too much about the quantum case? Is because you can do further simplifications beyond this once you allow superposition. The circuits, they work, there is nothing wrong with it, but you can simplify it more. And that is where the advantage of quantum logic will come in. So our point will be at some stage to come back to this and figure out what are the extra simplifications that are possible. Whatever is here is sufficient. You can improve on it and save something more. That is the goal of quantum algorithms.
But simplification is the only advantage in quantum case, or the speed is also
You can save on various things. The point is whatever simplifies you will be able to use it. It can save in space, it can save in time. The question is, well, find the schemes which will do that job.
So when you say slightly going back, still the work area for 1 to 2 can be released.
Yeah.
Do we have a mathematical formulation for how it is released, or it is the same?
You can write down explicit transformations. So now at this stage it is convenient to give a concrete example of the reversible logic. It's a theoretician's computer, in the sense that everything is taken to be ideal and you can demonstrate that it works. So it's a proof of principle. Nobody is going to make this computer. Okay. But there are all kind of complaints about reversible logic in the history, mostly because of no proper understanding of the second law of thermodynamics and what happens to entropy and things like that. And once it got resolved, the explicit example was given, well, then you cannot question it anymore. It does the job. So what is a billiard ball model? It is constructed as a set of balls which are colliding on a billiard ball table. And the only interaction is the ball will either collide with the boundary or they will collide with each other. Nothing more than that. And one can show that that is enough to do whatever computation you want with the Boolean logic. So what is the idealization? Well, one is that all these balls running around, there is no friction, no loss of energy anywhere. So all the collisions are taken to be elastic, energy is conserved. When it collides with wall, the momentum changes, but the energy is still conserved. And where do the operations come from? They come from change in momentum. Energy is conserved, that is no cost anywhere at all. But the change in the momentum somehow does your computation for you. Okay. So this is a fully elastic collisions, no loss of energy, and change in momentum performs computation. So we will now discretize it. The binary logic. We are not going to deal with continuous variables. We'll put it in a simple form. So let me draw something on a table, and then there is a grid which is as well as I can draw it in some sense. Not working out too well anyway. The grid is supposed to be at 45 degrees. That didn't work very well. Let me make a better attempt. So it has to close in a certain sense. So the whatever balls they're bouncing around, they will remain on the grid. So the trajectories of the balls at plus or minus 45 degrees and reflectors and boundaries are horizontal and vertical. Okay. So that is the scheme, and so the circuit can be made that it is completely closed. It cannot go out where it is bouncing around. I need something more, which is that how fast the balls are moving has also to be controlled. And the easiest thing to do is in one clock step, the velocity of the ball is so that it moves from one grid point to the next. That is a clock. So in one time step, the ball go from one vertex to next, and this means that the speed is fixed. Okay. 1 unit per time, whatever it is. The directions are still flexible in the sense that it can be going this way or it can be going that way. Speed doesn't change. Yeah. They are supposed to be squares to the extent of my drawing. Okay. These are the only angles, 45 degrees, and these are verticals. What more do I need? Well, the collisions with boundaries are taken care of, but the balls can collide with each other. Okay. So I have to fix that after the collision, the balls will still remain on the grid. And so now let me draw a little picture of a collision, that I have something coming on this direction, and of course the other one has to move in the opposite direction or orthogonal direction, which is here, and what happens during the collision is that it will come over this and it has to go in this direction, and a similar reflection will occur over here. Just ordinary description of a collision, they will be reflected according to Newton's laws, so change by 90 degrees in the direction. What does this require? That requires that when it collides, this must touch at a single point, and that is created the bouncing structure. You can look at it in many different ways. The best thing is to look at it in the center of mass frame, where they come with equal and opposite velocities and go back with equal and opposite velocity. And that means there is a relation between the diameter of the ball and the spacing of the grid. So they have to exactly touch at this particular point. So all this geometry, so diameter of the ball is square root of 2 times spacing of the grid. That's the diagonal of the square. No. All balls move on the same grid. And yeah, our job is finished. That this structure implements Boolean logic. There is nothing more required. Okay. And all we are using is elastic collisions between these two objects to perform a transformation on the corresponding variables. So now I have to assign variables. Where is 0 and where is 1? Okay. You can think of many possibilities, but the simplest one is that if the ball is present, we'll call it 1. If the ball is absent, we'll call it 0. Remember, there are other variables like the direction, etc., but the direction gets changed by the reflection procedure, and we don't have to worry about it if you're just talking about presence or absence of a ball on a particular location. And how will the computation proceed? We'll put whole bunch of balls on one of the tables and throw them in. They will collide at some stage and will come out on the other side. That will be the output. So identify absence or presence of a ball with 0 or 1. That is the mapping between mathematical variables and physical objects.
The number of balls also act as variables? Or
Yeah, you can throw in as many balls depending on the size of the input and the size of the table. If you have lots of balls, you will put them in different places. So the size of this grid is detected by the size of the input or whatever it is. Bunch of ones and zeros you start with. Throwing in some of them you might throw one way, some of them you might throw another way, etc. And so now let us look at just the same diagram. What does it represent? So there is a collision, and that I will interpret as some variable x and some variable y coming in. Okay, when both x and y are equal to 1, there will be a collision. But otherwise, there will not be any collision. What are the outputs? If x is 0 and y is 1, then I will get it just going through. When y is 0 and x is 1, this will just go through. The initial variables will appear on the other side automatically because the process is reversible. But what happens during the collision? That when both x and y are equal to 1, you will get something over here and something over there. And what are those somethings? It's xy.
How you are writing this x into y? If we knew already that both are 1.
Yeah, that's the only place when you will get some output over here. Otherwise, those values will be 0. And that finishes our job. The nonlinear operation of AND which required so much hassle to produce out of these gates, well, it came out. Output will be this time slice.
On the XY, those actually don't lie in the same line.
Time slice will be vertical. Okay, so this is in, out, and this is
So in the output, either we will use x into y or y, both in different situations. Simultaneously, like we cannot describe a uniform output, uniform expression, same expression for all output.
if x is 0 and y is 0, etc., everything will be empty, and you can call it whatever you want, but they are present in the possibilities available. The only extra thing is you have this nonlinear possibility available, and all it required was a single collision, elastic collision. Now you can work out what all going to happen with this other operation, 2-bit, 3-bit, etc. But the point is that a single collision has the ingredients to perform whatever we want. The caveat which happened with all this collision processes and reversible thing, that sometimes you end up with 2 copies of the results. The duplication, but that is part of the reversible structure, that sometimes you get 2 copies. So it happens. Because you cannot create or annihilate anything, something get created or annihilated only in pairs. Only in pairs, because this binary algebra is there, everything is modulo 2. So you can create and destroy things in pairs, you can't do it in steps of 1. So deeper mathematical structure, but it's all there. And now we can ask, can I make all those gates by putting in these collisions? The answer is yes. The ingredients are there, it's just a simple question of arranging various things, and I will give explicit what you call pictures of making those gates from these collisions. You need all kinds of things, because you need not just AND, but this control NOT, then the switch gates. There's a NOT operation which is also required. It requires a little bit of thinking. How will you make a NOT operation out of this? Because I identified the ball with just 0 or 1, and NOT means the ball has to disappear. It cannot just disappear arbitrarily anywhere else. The only you can go is it can go into a scratch space. And if your ball has to be created, well, it has to come from the scratch space. So even a simple thing like NOT requires you have to invent a scheme. But it can be done.
Scratch space means we will require additional bars. Additional bars will be required to construct scratch space.
Yeah. But that was the whole idea. I mean, this is a particular example. How much scratch space is required will be some description of this general principle. We are not trying to optimize the search space in any particular way, but we are providing a physical description that, yes, it is not just mathematical logic. You have something consistent with all the known laws. Actually, it is nothing but classical mechanics, Newton's laws, nothing more than is needed.
So this scratch space will be additional balls, or will be pockets of the billiard table?
Well, I'm using a spherical balls because that is what is used in a billiard table. If you have any other objects which can collide in the same manner, it will do the job.
This arrangement is classical, so can we do quantum computation with this? I think
No,
no. Obviously,
you cannot do superposition of the balls.
Can you just reiterate why not requires scratch?
Hmm?
Can you just reiterate why not requires scratch?
Because not means if the ball is there, it has to disappear. And if it is not there, it has to appear. Where can it go? Because I identified 0 or 1 with the presence or absence of a ball. Ball cannot just disappear from the whole structure. All it can go is it can go into scratch space, while in that particular location there is an absence. This is a conservation law, whatever it is. They have to be buried inside here, so number of balls is a constant, whatever it is. If you don't want it, put it in the scratch space, that's all.
How this
there will be a lot of lines which are empty initially. It's not that every possible location has to have a ball. There can be a lot of things which are empty.
Because more complicated bits are similar type of bits we must have. Are any operation corresponding to each gate? So they could have done all operations using this particular bit, or they would require any other type of bit.
You can imagine all kind of things. I'm illustrating this as an explicit example. It does the job. You want to play with more variations, go ahead and do it.
It will do all the jobs. It will do all kind of jobs.
This is a question of sufficient. I am not optimizing anything. You want to construct a different model, go ahead and do it. No complaints. Okay, but this is enough. It is not quantum. You can't do superposition of these two balls which I identify with 0 or 1. So it will not, but classically there is nothing more which is required, and that is why it is an explicit example. And I will give various details next time, because there is one more question which will come, that how I measure the output. Okay, we'll simply say the ball is there, you will call it 1. But in the classical physics, you should be able to measure the result without changing the state of the system. Okay, that is our understanding of a classical observation. It's different from the quantum case. That the state remains whatever it was, but you get a result. Can we perform that in this particular situation also? That ball will keep on doing whatever it was doing, but you get a result out. And that can also be done. It requires some amount of juggling around with this transformation, and I will illustrate that also next time. Okay, then this is where I stop.